Log on, tune in, find out. Another good idea from Cambridge.
Mizan Rahman from University of Carleton, Carleton University in Canada. He'll be speaking about probabilistic origin of some positive kernels associated with classical orthogonal polynomials in 1 and 2 variables. Thank you.
Well, if you don't remember me for my talk, which probably you won't, at least you'll remember me for being the only person to use this archaic equipment. I would like to thank the organizers for inviting me here for two reasons. One, the honor to be here among all these people and opportunity to learn something new. Two, the second time I'm in Cambridge. The first time was long time ago. You can imagine how long ago I was an undergraduate by looking at the way I'm using my slides. At that time when I was here, Churchill College did not exist, and the whole town was a bit grim place. First of all, the men's and women's residences were separated. Number two, the undergraduates and grad students all had to wear the gowns. Fortunately, I was an undergrad, so for undergrad there was a short gown. For the short gown, it was long enough for me. You can understand why. Thank God I was not a grad student, because if I were, I would have to wear the long one. So first I would look like Afghan woman in a long chadar, and secondly I would have to go to the laundry every day. Anyway, some people consider me as something of a specialist in special functions. I don't know about that, but to make it worse, I wrote a book with George Gasper, and so that probably qualifies me to be called expert in something. But I must tell you that my career did not really start that way. I did my PhD thesis in statistical mechanics, kinetic theory of plasmas and gases. So on my first sabbatical, at that time, of course, anybody who worked on the kinetic theory, all he or she did was try to solve the Boltzmann equation in one form or another. So we were all solving Boltzmann equation, going nowhere. And that is what brought me actually to London. This gentleman sitting here, he came from London today, Michael Hoare. He's a physicist originally in chemical kinetic theory, and so he had to use a lot of molecular models, interaction of molecules, and at the same time he was also interested in something that I was doing, like singular solutions of Boltzmann equation, okay, which is he used to call Rayleigh pistons. So while I was pushing pistons, he was busy with some other of his graduate students constructing some interesting probabilistic models. And somehow they got stuck somewhere, mathematically speaking, and so sought my help. And I looked at it, I said, beautiful. This is one way to look at the special functions and orthogonal polynomials. The standard way I knew at that time, that was in 1970s, early 70s, was through differential equations or difference derivatives and so on. But here we got to approach the orthogonal polynomials from the point of view of integral operators. So, that made it look more exciting, particularly when some known results and special functions appeared in his work, but in a more physical context. So, that was much more attractive to me. So, sooner or later I got somehow sucked into the whole field. I suppose that is the story of many of you, how one can get away from his original field and hooked into something else. So, anyway, so this is how I started. The initial model that we considered is the Earn model, the very basic one. What's the number of ways, call it G sub n, of permuting n unlabeled objects among S cells is, by simple combinatorics, is n plus S minus 1, choose S minus 1, and we wish to write it in the more in the form which is appropriate for use in special functions, namely the Spokhammer symbols. So, with this definition, if you want to find the probability of finding I of capital N objects in a subset of P in a P plus Q cells, and if you want to find the probability of finding P, exactly P of them in I cells, that this is the probability of that is normalized, and this is distributed in an unbiased manner. Now, starting with this, our paper starts with this, and this was published in 1977 in the Journal of Mathematical Analysis and Applications, SIAM Journal. No, sorry, Journal of Mathematical Analysis and Applications. Okay, so story doesn't end there, of course, thank God. So, we considered one more step, a dynamic Earn, so-called dynamic Earn model. What does it mean? You get n balls and 3 subsets P, Q, and R of total P plus Q plus R cells. I have to find a way to store it. So, here is a little picture. You have I cells, I balls initially in the combined cells, 2 combined P and Q, P plus Q, and the rest of them n minus I placed in R cells. Now, the P plus Q, the I balls in P plus Q cells, you now randomize and then separate the P cells again with its own contents. So, let us say the contents now is K in P cells and I minus K in Q cells, where R cell still has the original n minus I balls. The next step, this I minus K, the cells with I minus K balls, you now combine with the R ones, and now you have got a total of n minus K balls. Randomize again, and then separate Q balls again with the new set of contents, right. So, call that J minus K balls in Q cells and n minus J balls in R cells. Go back to the original position, combine P and Q and keep this n minus J separate in R. Now, the new number of balls in the P plus Q cells is going to be J, K plus J minus K. What is the probability of the going from the initial state I to the final state J? Okay. Now, that is a simple calculation. This is the convolution of this is the first order, generates the first order Markov chain on the discrete sets 0 to n with the transition probability, which is the, you can see easily the why how this is constructed, get all sum over all possible k's running from 0 to whichever is minimum of I and j, and over the product of the initial p f sub p q of k I, f sub q r of j minus k and n minus k, and use the formula beforehand, and lo and behold you get this kernel, and which you can write in terms of the hypergeometric notation, not that it helps at all, but just to I have to justify that I am a hypergeometric man. So here it is. Now, the property of this kernel is fairly straightforward. First of all, stochastic matrix, so it must add up to 1. So that means the left eigenvector of this kernel is 1 1 1 1, this unit vector, whereas the right eigenvector is going to be the what we call the stationary state. Okay, and this it can be easily seen that this phi naught is this distribution capital F, the j balls in p plus q as p plus q cells, and the rest of them are in R cells. Now, you can iterate this matrix n times to get see what happens after n such trials, and get the n step transition probability, and you know this is just simple linear algebra. How to compute that? You compute the symmetric matrix, you can symmetrize it, and then get the symmetric matrix positive, the roots must be real, and etc., and you construct the orthogonal matrices. Diagonal matrix is lambda for all the eigenvalues, and there you are, you have got the nth iterate. So, what is now the eigenvector, nth eigenvector? Now, how do you go about that? So, that is interesting. You can either say, okay, the capital F function, I can see that this is related to the negative hypergeometric distribution. So, I also know that the Hahn polynomials are the orthogonal polynomials with respect to that weight function. But suppose we do not know that. What we can do, and in fact what we have done in that paper of ours, is to sort of factor that kernel into a product of two matrices, one whose action is to lower the degree of the polynomial, and the others is the second one is to raise the degree of the so it is like a ladder operators, and this is more or less the same idea that you apply for special functions, orthogonal polynomials with respect to the derivatives. The sum of simple derivative will lower the degree, and the weighted derivative will raise the degree. So, anyway, so we use that to factor the whole thing, and this is for q equal to 1, just to have an idea of how to go about it, and then it is easy to this is, by the way, if you, I'm sure most of you know what Hahn polynomial is. This is the Hahn polynomial, and it has the orthogonality property. You will see any handbook, Bateman manuscript project is the source of everything. So, you get there, this is the normalization constant. In general, this is the eigenvalue problem, and by factoring the kernel, we were able to prove that the Hahn polynomials are the eigenvectors and these are the eigenvalues. Okay. And so, since this is everything is nice and simple and just a simple matrix, all you have, just write down the kernel, the nth degree iterate of the kernel k sub super n, which will be the sum of this bilinear sum with lambda sub k, the n, this is the eigenvalue to the power raised to the power n. And it's very easy to check, of course, it has to, the 0th order for n equal to 0, it has to be the delta function.
That's off the bottom of the screen.
Beg pardon?
You're pointing off the bottom of the screen.
I'm sorry. Okay, thank you. Case super 1 is the original kernel, and when you take the n going to infinity, when n goes to infinity, lambda goes to 0, and so you get simply the original stationary distribution.
Lambda goes to 1.
Yeah, sorry. Thank you. Okay. Now, you can take a lot of limiting process here. We have got some freedom. Suppose we want to go into the continuous limit. So, what do? You just scale the sizes. You put capital N, the number of balls is multiple of some x, and the I, the state variable I, which is the in here in the previous model, it is the discrete number of balls. So, you scale it by t. So, t times x, little x, and then let t goes to infinity. So, in the limiting process, you see, this is one of the reasons why we use the Pochhammer symbol. Now, you do not need to go to the starting formula, get it, etc. You just take the limit right away. Here you can see that. So, and what you get? It is the standard beta distribution. Okay. So, we write it this way. And what happens to the kernel? The kernel, now the sum becomes an integral from 0 to minimum x y with this different rather interesting looking integrand. So, we call it k, capital K. Our function now x and y are allowed to be continuous variables. What happens in the same limit to the Hahn polynomial? Well, it's very simple, pure formal reasoning. It becomes a Jacobi polynomial. Okay. Once again, you have a spectral representation of that, which you can write down in this manner. This again has other limits. not the continuous one, but from the Hahn case, we still keep I and j discrete and finite, but let n go to infinity in such a way that n divided by n plus r remains constant. This may represent a heat bath with a temperature constant. Okay? And this will give rise to the Meissner polynomial, which the Meissner polynomial is defined by this 2f1 series. From the Meissner polynomials, we can now go to the Laguerre, rather from the Jacobi case, we can go to the Laguerre process, which will be obtained by taking x going to infinity, r going to infinity, and well, but r is what is r? Is now theta times capital X. The limit of the kernel is now involves an exponential function. So, in particular, when little theta equal to 1, you get this kernel. Now, what is the big thing about this kernel? Because historically, this is the kernel that attracted Mike Hoare and his collaborators, his students Cooper, because this one you will find in the handbooks, especially in particular Bateman manuscript project, second volume 2, orthogonal polynomials. This was obtained by Arthur Ardeli in 1938. At that time, I don't believe that he knew it would have a physical significance. In fact, it is the physical significance of this kernel that attracted the physicists like Michael Hoare and also myself. This is the spectral representation that is given in Ardeli's work. Okay. Now, there are of course other limits, for example, Kraschuk limit. You can do that by, again, in the Kraschuk limit, you do not go to infinite size, you keep capital N, the finite number, but you let p, q, r go to infinity in such a way that r upon p plus q plus r goes to a non-zero number, which of course will be less than 1. If you do that, you get the Kraschuk polynomials. So, based on these informations, by the way, there are other lower limits like the Chardier limit. Then from the Jacobi you get the limits like Laguerre we have got. To Laguerre you can get the Hermite polynomials. So, you get a whole tree of some classical orthogonal polynomials. So, according to this idea, what Mike did and we did in our paper, we had a flow chart going from starting from Hahn polynomials and going in different limits to different places, covering a whole fabric, a whole field of known classical orthogonal polynomials. So, he had a sort of tableau there. And with this tableau, armed with this tableau, Mike was invited, when he was invited to give a talk at Oberwolfach in 1985 or something. People were just, they ignored everybody else and swarmed around him to get that copy of the tableau. So, it was a rage at that time. That was in around 85. It's earlier? Yes. I don't remember that. I don't think so, because I was there in 1984. He went there after me. No? right? Anyway, doesn't matter. So, what happened in the meantime? Now, you will notice, of course, this tableau at that time was exciting, because 1978, from Wilson's thesis, came out the basic information that the physicists' 6 J symbols, which we all know in quantum mechanics, angular momentum theory in quantum mechanics, is a very important it's called the Raka coefficient. Okay. He proved that this is in fact orthogonal polynomial orthogonality. The orthogonality of the 6 J symbols is simply a polynomial orthogonality, and hence the name Raka polynomials. From there, they went on to Q Raka polynomials by introducing a Q parameter, and from there soon the continuous analog came along, and that became the Askew-Wilson polynomial. The Askew-Wilson that paper came out in 1985. Okay. So, around 85, 86, there was a craze again to christen the tableau as the ASCII tableau, okay, because everything discrete originated from Q, the classical family originated from Q Raka, and the continuous family originated from Askew-Wilson. So, it is a big long tree, and the tree is now complete, more or less. So, in this whole excitement of this new find, poor Mike's work got lost. So, I always maintain, in fact, not me really, it was ASCII. He knew about it. He always insisted that tableau should really be called ASCII whole tableau. So, I just wanted to keep the record straight. Anyhow, now this is not the main topic that I am going to talk about today. The main topic is something else. In 1983, Mike and I got involved in a different kind of model, which again it is basically his work, which he called cumulative Bernoulli trial. The idea, let's see, I'll use the language of, say, a drug testing experiment. So, let's say we have a population of any species, humans or animals or whatever, and there is a disease going around. So, there is a testing going on for a new drug that came out, whether how effective that drug is. So, let us say we have a sample of people that has been taken, and out of that sample, I of them has been marked for testing. Okay. And so, the drug is administered, and the remaining n minus I of them are kept away. Some of them are maybe infected, and some may not be infected. So, let us say I of them are known to be infected. And so, the drug is administered, and let us say the probability that the drug will resist the treatment, let me call it rather in a sort of perverted way, that is a success. And let us say the success is k, the alpha. The probability of success is alpha, and the number that remains infected is k. So, the number which supposedly has been cured is I minus k. And now, you join this I minus k cured persons with the other remaining sample, and the total of them it becomes n minus k. Now, out of this n, oh dear me, I am so sorry. old age can play tricks in many ways. Okay. So, you have got this n minus k, which contains both infected and freshly cured, supposedly cured individuals. But now, let us assume that the probability that these so-called supposedly cured individuals and otherwise untested individuals will have equal probability of once being reinfected and the other being getting infected. So, let us say that you are testing the drug again to this all of this n minus k of this, and the probability that j minus k of them do not get cured is beta. So, that the n minus j of them will be cured with a probability 1 minus beta. Okay. So, the final outcome, you add this to that, the final outcome in this non cured ones is j, and the cured ones is n minus j. What is the transition probability starting from I to the final state j? Well, this is again the transition kernel is the convolution of the binomial of distribution of k individuals out of I with a probability alpha, j minus k individuals out of n minus k with probability beta. Simple. And if you want to write down in terms of the hypergeometric notation, then this is simply 2f1, and the probability parameters appear in the argument in this way, where b the binomial distribution is of course this familiar one. Now, once again we proved that now of course this is very simple trivial question, because we know about anyone who knows about the Cauchy polynomials will know that these solutions are simply the Cauchy polynomials, and the eigenfunctions are psi n, this is the Cauchy polynomials, and this eta is now combination of beta and alpha in this manner, beta divided by 1 minus alpha times 1 minus beta. That was pretty simple, but of course, in that paper 1983 paper, we introduced a lot of other ideas too. Now, naturally one gets greedy if you have solved the case of testing the drugs in one set of individuals. What stops you in trying the same drug in different sets of, let us say we group the infected individuals by their say sexes or their ages, and different ages may have different probabilities of getting cured, right. So, accordingly, let us say we take one set I 1, another set my wife would have, unfortunately she is not, she passed away a few years ago, but she would have been quite amused. Of course, she would have known everything. And anyway, so I 1 and I 2 are the two sets we start with of two groups of people on whom the drug has been administered, and k1 of them have survived from the have resisted the drug out of the first set, and k2 of them out of the second set. So, presumably I 1 minus k1 of them have been cured, and I 2 minus k2 of them have also been cured from the second set. Now, you keep them as they are. This so called cured individuals now you group them again, you combine them with the general population that have been left alone without the drug being administered. Okay. So, this has been done say with a probability alpha 1, this with the probability alpha 2. And now, when you have combined them together, you get n minus k1 minus k2 individuals, which now contains the otherwise untested ones plus the ones who have supposedly been cured. But again they have probability of getting infected again. They are again the same susceptibility as there, because that is what we are assuming. So, administer the drugs, what you get, let us say J 1 minus K 1 of them in the first group, J with the probability beta 1, J 2 minus K 2 of them with the probability beta 2, and therefore, these are the ones that have resisted infection, drugs, and these are the individuals who have been cured. So, add this J 1 minus K 1 to the first group, J 2 minus K 2 to the second group. So, the total will be now J 1 and J 2 coming from this original I 1 and I 2, and n minus J 1 minus J 2 coming from this. Yeah.
But in this case, there's a bias, because in the previous case, where the I were representative of the general population of the n's of the n minus I, it was fine. But here, the I1 and I2 have some property intrinsic, and among the n minus n I1 minus I2, presumably the proportion was the same as the I1 and I2, or maybe not. But now you have a total bias, because the n minus K1 minus K2 have a completely different repartition of the I2 and I1 class.
Well, this is the reason we'll say that the probability of going from in this way is now the trinomial distribution.
Okay, so you keep the memory.
Yeah, trinomial distribution.
I say something.
Yeah.
I prefer the model of the poker dice. You've all played poker dice, I think, with 5 dice. And you throw them, and you can throw kings or aces. Now, that obeys this exact same model, probably getting so many kings, so many aces. And it's interesting because they're anti-correlated. The more you get of one, the less chance of getting another. So I think that's the simplest way to describe it. But of course, drug testing is much more important than
Yeah.
poker dice.
Poker game, I don't play poker, so I resisted it. So, the K is now you can this is now a double series, and there are 4 parameters now. This is important, 4 parameters, alphas and betas, and they are in general they are independent. Now, the question is, we have a trinomial. For the steady state conditions, we can figure out the steady state distribution, which is a trinomial distribution. The question is, what are the eigenvalues and eigenvectors? I thought it would be easy. Well, some kind of Cauchy polynomials. So, that was the problem we started thinking about 1985. And 20 years gone by, we couldn't crack it. So, you know something that as being researchers yourself, when you solve a problem, it is easy to forget about it. But when you cannot solve a problem and you think it is important enough, then you will never forget it until either you die or you solve it, or you prove that it cannot be solved. So, in now you see the traditional method of starting with the weight function and then using some kind of Gram-Schmidt way of constructing the polynomials, that would be attractive, except that you would have only 2 parameters, whereas here there are 4 parameters. And this important little point, which seems like so trivial, just didn't hit me until much later. I realized that how can I fit something 4 parameters into a scheme where only there are 2 free parameters. So there is no way you can do that. That is where suddenly it struck me that let's look somewhere else. You see, as I said, Raka polynomials are, as Wilson showed, are simply the 4f3 polynomials, 4f3 polynomials, which come from the 6j symbol, which is the quantum mechanics in you have 3 angular momenta, you combine them, you have a coefficient in expansion in a certain basic vectors, and you get the coefficients. These coefficients are the Raka coefficients. So they have a nice single sum representation. The next level, so we know from there we get the Raka polynomials. From the Raka polynomials we get the Hahn polynomials. From the Hahn polynomials we get finally to the Cauchy polynomials. Now the next level in the quantum mechanics is 9j symbols. It's 4 angular momenta combination. Now 4j symbols is not so simple. 9j symbols are not so simple. It is, this is one 6j, another 6j, another 6j. There are in fact 4. This is a quadruple sum. So it's a pretty complicated stuff. For the physicists, they only mostly look for the symmetry problems, symmetry properties, and some other physical significance. But for mathematicians, it is not a simple thing. I mean, it's complicated. It's simple, but I would say simple, but it's messy. What is important thing is that it is known to be orthogonal and orthonormal. In fact, this is the orthonormality property. So if this is the orthonormal property, and if 6j symbols turn out to be polynomials, my instinct was these also one should be able to convert it into a polynomial system. And if so, then I get the 4 free parameters here that I wanted. So accordingly, following Wilson's scheme, I normalized the parameters in a different way, and that was, of course, just wanted to show you what is the Raka polynomial. These are the Raka polynomials, and polynomial orthogonality of 9j symbols. This was done by several people. Sorry, this is by Wilson. Now the next question is for the 9j symbols. 9j symbols has been a mystery for the people in orthogonal polynomials and special functions, because it's challenging, because some people felt, including Dick Askey, that one should be able to express it in a double series. So that is the wild goose we were all following. It was, some people was able to express it in a triple series, including myself. I didn't publish it, but other people did. But it turned out that is absolutely no use, because you cannot establish the polynomial character out of that. Anyway, so if you write it down in the whole thing, it is not very pretty, but it is very important. The form that I am writing here. Oh, time goes very quickly. Sorry. So orthogonality properties are this. This is the orthogonality. This is the dual orthogonality. Now, what I do in the proper cross-check limit, I take all the parameters a, b, c, d to infinity, such that the zeta goes to infinity and p1, p2, p3, p4 remains independent. Once you do that, the polynomial you get is this thing, and you can see that this is a this is a form of cross-check polynomials, okay? Except, sorry, there is some term missing. This line point, I am sorry about that. This should be u to the power t to the power I, u to the power j, v to the power I. I am coming to that in a minute. These 4 terms are missing here. Somehow it was a mistake. The powers, the t, u, and v and w, I am talking about these ones. Okay. And you notice that the symmetry of these parameters in all these variables t, u, v, and w. These are the 2 parameters involved in the trinomial distribution, which is the stationary distribution. I have to rush a little bit. And with this, what did I succeed in achieving? Because it can be transformed. So, what I did, I tried to apply to see if these polynomials satisfy or become the eigenfunction of that kernel that I started with. Sure enough, it does. And the eigenvalues turn out to be a little more involved now, where delta is this quadratic thing, and the lambdas sub m n are the eigenvalues. Okay. Now, I thought I am the first one to find this nice looking quadruple series representation of 2-dimensional cross-check polynomials in 4 essentially different independent parameters. But then in another meeting, Matsui Nomu, he pointed out to me that Gelfand and Aomoto had found more general or multiple n-dimensional stuff in 1994 in an algebraic context. And Mizukawa actually proved the orthogonality indirectly again in 2004. So, okay, so it is not a new result, but I would say the parameterization of these polynomials, I did not see it in their work. Whereas, in the parameterization of these variables is a very crucial stuff, particularly say in view of the recent work that Alberto Grunbaum and myself are doing, namely the 5-term recurrence relation that these polynomials satisfy involves p's and all the 4 p's in a very strange way, and we need all 4 of them. Okay. Anyhow, what did surprise me is the fact that if you take limit a going to infinity, for example, then this whole 9j symbol simply collapses into a product of 2 Hahn polynomials. One of them is a Hahn and the other one is a dual Hahn polynomial. That frankly I did not expect, but whether I will call it a nice result or not, I do not know, but it is for me it was a surprise. The same thing happens if you take d going to infinity, but for b going to infinity, sorry, the original FM, the 9j symbol. again the same thing happens. One of them is Q Han, sorry, one of them is Han and the other is one is dual Han. Now Q analog. Some people, do I have time? Some people, especially my good friends, make fun of me, saying that I am a person who is compulsive obsession with Q is become almost like a disease. That whatever anything on site, I will try to find a Q analog of that. Well, it's probably not that kind of mark, but nonetheless, my interest does occur there. So this is the Q Raka polynomials of ASCII and Wilson, and these are these notations. The Q analog of the 9th symbol, that is another mystery. Alisoscus and other people, quite a number of people in fact worked on that in the context of group theory and got some results, but they did not prove the orthogonality. In fact, if the stuff they started with, they took has a q to the power n choose 2 factor there in here. With that factor, you can go nowhere. In fact, I did myself, and I found that they are not orthogonal. So what is the mystery? It took me a long time to figure it out. In fact, you have to have some. This is this what we call the well poised part of this series, which has to have this kind of parameter involved there. No q to the power n choose 2 must appear. If you do that, and then simple Q series analysis will give you the orthogonality. And this in fact is true not only for tau equal to -1, which would be the case for the ordinary 9th symbols, but also for tau equal to +1, which would be, I would say, something different. And I also proved it is easy to prove the dual orthogonality too. And I found the explicit polynomial form of this Q9J symbol. You can see this is the state variables x and y, m and n are all upstairs. Okay. So, and this is something that also eluded a lot of researchers. Here again, surprise. If you take d going to 0 or d going to infinity, completely breaks down and becomes a product of 2 3-phi-2s. There you are, my friends. There are a few other things I could have said, but I think I've run out of time. Thank you.
So just to prove that there are people with worse diseases than you, what about biorthogonality?
Well, biorthogonality is here. There is a way to obtain a biorthogonal system here too.
Okay.
Yeah. In fact, I could have done it. In fact, in the biorthogonal system, you can have the proof goes exactly the same way, except that you can have very arbitrary parameters coming in there, which would be, in my view, would be spurious. It would have no significance. I prefer an orthogonality when I have, rather than biorthogonality.
Well, to follow up, of course, the reason I want biorthogonality is I want an elliptic analog.
Oh, I see. Yeah, right. But at the same time, here, what will stop you from going into the elliptic stuff, as long as you go from 4phi3 to the 8phi7. This is what I was going to suggest, that the next level of research would be for the people in the elliptic say stuff, is to first of all take the 8phi7 form of 4phi3s and then take the elliptic form. See if it works.
Yeah, this is a historical question. How did Daly come to this kernel identity? You know?
Well, now I don't know the history, but at that time, it was in 1930s. Quite a few other people were involved there too, and in fact, I think he was able to use the fractional derivative approach on the Laguerre polynomials to find that Laguerre polynomials are indeed the sort of solutions, eigenfunctions of that kernel. Okay. That was his result. But at that time, in those days, they were all using the Riemann-Liouville fractional derivatives ideas in contrast to the ordinary derivative ideas, and getting some nice results as integrals rather than differential equations.
I could add something to that. If you take the single integral operator, not the convolution, that was found by somebody called Carleton in 1938. I've got the reference if you're interested. And it was in connection with Emmy polynomials, actually.
I suggest we stop here and we thank Mizan for his work.
Thank you.